Okay, so today we are starting into applying Newton's second law of motion. Okay, with applying Newton's second law of motion, we do need to take the opportunity to take a look at what the equation is, how we're going to actually get to it. One of the big things that we end up focusing on is the concept of net force. Okay, we need to consider all of the forces that act on these objects. Okay, you'll also see you have a fun little table to help organize your information. Obviously, we'll kind of see how things go. So let's just start by jumping right in. Sample problem number 1. Ellen, who is on the right, is holding a stuffed dog with a mass of 0.30 kilograms when Sarah, on the left, decides she wants it and tries to pull it away. So 2 kids fighting over a stuffed animal. If Sarah pulls in the dog with a force of 10 newtons, Ellen pulls right with a force of 11 newtons. We want to be able to find out what is the horizontal acceleration of the dog. Okay? Now, there are some other factors that are at play, but effectively, is this dog, the stuffed animal, going to accelerate along the x-axis or y-axis? X-axis. So I'm going to oversimplify this problem, okay? But just as a means for us to know what our process is going to be. Okay? So the first thing we are going to do is to draw a very simple free body diagram to show, in this case, just the horizontal forces. Now, I know that we do not have, technically we have 2 applied forces. In the problem, though, you can see based on the picture, okay, they label them as F1 and F2. We will do the same. Okay, so it says Ellen pulls to the right with a force of 11 newtons. Is that the greater force? Absolutely. Okay, so let's go ahead, we'll draw that arrow, and I know it's only 1 newton of force greater than the other, but we'll just go ahead, we'll make sure that we make the point to draw that a little bit longer than our force that is acting in the opposite direction. Now, I fully understand this stuffed animal is going to have a weight of which we would diagram. Okay, that we're not going to worry about. Okay, so step number 1 is going to be to go ahead and draw the forces that we see. Okay, next, we are going to go ahead and use our table. Okay, what is the table going to be used for? It's going to be used to list out the forces that we have and figure out their components. So F1 and F2. Do either of these forces have vertical components? No. Anytime that we're looking at this, if we see that we have forces that we know that one of their components would be 0, start by filling in your table there. That makes this really easy. F1's y component would be 0. F2's y component would be 0. The nice thing about these forces is automatically we know what the quantities of forces are. We don't have to do any further calculations to figure out what we need. Okay, so F1 is the one that's pulling to the left, so we're just simply going to put that in as a 10, correct? No. Negative 10. Why is it negative 10? Go to the left. Okay? F2 would be positive 11, correct? Absolutely, because that one is going to the right. All problems are going to be a little bit different in the total number of forces that they have. This one and how we're solving it, there's only 2. You could have a problem that could have 3 forces, 4 forces. I'm not going to necessarily give you those examples right away, but we could have something that has 10 different forces acting on it. Okay? Step is figure out the x and y components of our forces. Next step, we come down to this line down here where it says sigma fx and sigma fy. You're all intelligent human beings. What does sigma fx mean? Michael, what are we going to do? Absolutely. We're going to take a look at all of our x components for our forces, and we're going to add them up. Really difficult stuff here, people. Negative 10 plus 11 gives us 1 newton of force. In the upper part of the table, I'm not so worried about you putting the label. Okay? But just once we get to this stage, because this is kind of the last point where we're only dealing with force, I want to make sure that we do have that labeled there in newtons. Sigma Fy, that also should be pretty easy. 0 newtons. So before we go any further, I want to kind of state, what does sigma Fx being 1 Newton mean? It means that after we consider all of the forces that are acting on this object, the net result of that is a force that pulls with a quantity of 1 Newton in what direction? To the right. And based on our free body diagram, shouldn't that be the case? Absolutely. Okay? So, next step is we're going to solve for the acceleration. And I've started here, at least in terms of the samples, and giving us a head start on it. This is just the rearranged version of Newton's second law, where the horizontal acceleration, AX, is going to be equal to sigma Fx divided by our object's mass. Well, that is going to be 1 Newton, which we just found, divided by the mass. And a friendly reminder, mass has to be measured in what? Kilograms. Is it already given in kilograms here? Yeah, pretty easy to do. Okay, so then we just leave it as 0.30. Pluggy chuggy, figure out what our acceleration along our x-axis is going to be. Carly, what do you get? 3.33, and this is acceleration, so it would be meters per second squared. And actually 3.333 meters per second squared. Now, I'm also okay with us doing it at this stage, but we can look at it with a sum of the forces at the moment where the y-axis is 0. If the sum of the forces is 0, that means that the acceleration should be 0. Now, this just happens to be an example where we don't really have anything that we're considering along the vertical axis, but understand that just because the sum of the forces is 0 does not mean that there aren't any forces that are active. Okay? We could have forces that work kind of in tandem with each other, and they could be the exact value pointing in opposite directions that could negate the effect of each other. Pretty simple problem. Okay, so kind of rewind this so we know what the process is. Okay, number 1, free body diagram. Okay, we'll go ahead and draw the free body diagram to get what we need. We have to have that to visualize what's going on. Then we'll list out all the forces that we have in our force table and find their components. The next problems that we're going to do, we're going to have to find some components, and that's okay. So we'll fill in the data table. Sum the forces, solve for the acceleration. I think it's pretty straightforward. Okay? So, sample problem number 2. Okay? We are going to have this change a little bit, but what I'd like you to do, take a minute, go ahead and read the problem, and all I want you to do is just to draw your free body diagram. Pay close attention to the verbs and adjectives placed in that problem. It is an applied force, back to that first question, okay? But the problem itself, label it as F1, F2, it's okay to just label it as F1, F2. Okay, the list of forces that we put together last class is not the only combination of forces that we can have. There are all sorts of different labels we can use. Okay, and we're not even necessarily even limited to numbers. You have force A and B. That can also just be applied forces, but we'll just call it maybe 1A and 1 would be B. All right, hopefully we see that our free body diagram should be drawn on an incline. So our object should be also drawn on an incline. And Aaron, what's one of the forces that we have to draw? We have weight. Where does it start? Center of mass, and it points straight down. As we're going to find out, that's going to be a very important piece of what it is that we need to do. And what's another force that we need here? We do need the normal force. Where does it start? The middle of that guy. I'm sorry, I don't know what that guy is.
Like to the left of the line.
To the here?
Yeah.
Okay, that's called the contact surface. Good, and it's going to point where? Okay, it is perpendicular to that contact surface, so it is going to point in this direction. Okay, so there's our normal force. And by the way, I also need to state and reiterate to note what we talked about last class. Normal force sometimes is treated as lowercase n, capital N, if it doesn't really matter. Okay, with those two forces, okay, we would want to go ahead and put them into our table. Okay, so we would have the weight, we would have the normal force. There really aren't any other forces in this problem. Why? We're told that this is a frictionless surface. So therefore, we're not going to have any forces to diagram in that regard. But we have an issue before we even get going on any of the math. This is something that we absolutely have to wrap our heads around. Where would this object accelerate? Not a complex question. Where would it accelerate? Isn't it going to go down the inclined surface at an angle? Okay. That's kind of a problem for us because what are we trying to find at the end? We're trying to find the acceleration of this object at an angle. So here's what I want you to envision, because here's what we are going to do. Okay? So you would normally have your x and y axis just like that. But what we need to do in this problem is we need to rotate our x-axis so that it lines up with our inclined surface. So we will actually take it and rotate it in that way. So what does that do for us? Okay? That will give us acceleration along an x-axis. That will become our x-axis. And perpendicular to that is going to be our y-axis. So no, the x-axis in this problem is not going to be perfectly horizontal. The y-axis is not going to be perpendicular to that point. Okay? We do need to rotate it. But here's the thing. When we rotate it, what angle did we rotate our x and y axis by? It will be the exact same angle as to what the incline is itself from the horizontal. In this case, it's 30 degrees. Because here was our x-axis along the horizontal. Now we're going to line up with that. So that ends up being an angle of 30 degrees. Everyone follow what we're doing? Does everybody see? And now would be a chance to say no. Does everybody see why we had to do that? Okay. One thing that we then need to do, what becomes an issue for us, not necessarily our normal force, but our weight. Because we're going to have to find its x and y components, now it is going to have a y component that will come down like this, and yes, I would like for you to draw it, and an x component that will come like that. And we are going to label this as FGY and FGX, where the hypotenuse effectively is labeled as the FG. You don't have to move it if you still have it down near the end of your arrowhead, but that's where it's going to be. Okay, before we go ahead to jump into this problem, okay, we don't know the normal force. That's one of the things that we're going to have to find in this problem, and I'll show you how we do that in a minute. But we are going to start by calculating, because we do need to find FGX and FGY. I don't know if you remember, back to your notes, this would be a good way to review. How would we calculate weight? Fg is equal to what? Mass times acceleration due to gravity, m times g. Okay? So if we wanted to find the hypotenuse here, it would be m times g. But here's what's kind of unique about it. Before we rotated our x and y axis, our y component, FGY, would have lined up perfectly with the vertical. Okay, it would have lined up right here. So if it was just a regular problem on a horizontal surface to calculate an object's weight, we would just do m times g. Done. But when we rotate both the x and y axis, the angle that is equivalent to the angle of our incline is actually up here. It is between our hypotenuse and our y component. which this is one of 2 times all year that our x component and y component do not follow the same trig functions as to what we've done earlier in the year. Okay, so when we do that, f g x would be equal to m times g, which would give us the value for our hypotenuse. But let's take a look at where the x is. In terms of a right triangle, is it the opposite or adjacent side? It is the opposite side. And we know the hypotenuse in mg. So, what trig function uses the opposite side and the hypotenuse? Sine. So this, to find the x component, would be mg sine theta. And I know many of you have probably conditionalized yourselves to say, the x component is cosine, the x component is cosine. It's not in this case because of where that angle is. And if we did that, well, we should be able to find FGY, since that now is our adjacent side, m times g, which is the value of our hypotenuse, multiplied by what trig function? That would be the cosine theta. So, we know that this is a 20 kilogram block, so let's spend a minute, and I want you to calculate FGX and FGY, and yes, you should check your calculators to make sure you are in degree mode. Oh, one more thing to add to this. For reasons we will see in a minute, when you're going to plug in G for these problems, you will just plug in as 9.8. Do not plug it in as negative 9.8. We will assess the direction in a minute. So we'll just do 20 times 9.8 times the sine of 30, 20 times 9.8 times the cosine of 30. All right, Kivash, help me out with the FGX. What do we calculate when we get FGX?
98.
Okay, we should get 98 newtons. Does everybody get that? Yes? Okay, we should if we know our unit circle. We understand that when we do the sine of 30, it gives us half. Half of 20 times 9.8 would be 10 times 9.8, 98. Good, done. Carly, what about FGY? 169.741. Good? Okay, one more thing before we go, and this is an absolute necessity here. We need to check whether things are positive or negative. And think of it this way. This here is our starting point. This here is our finishing point. So FGY, to start here and go this direction, would we consider that to be up or down along our y-axis? In a downward direction, or a negative y direction. So that means our y component needs to be negative. The way that this incline is set, we would then go from here, okay, and go towards the positive x direction. Do we see that? Okay, so that would remain as a positive 98. We found our components for our weight. And I will say that for anything that's not on an inclined surface, it is easier. That's kind of the one thing that's a little more complicated in this problem. Okay, now let's take a look at normal force. Normal force is parallel to what axis? Parallel to what axis? It is parallel to our new y-axis. Okay? So it's going to have some sort of y value. We don't know what it is yet, and I'm going to show you how we find it. Does it have any x component? No, not in this problem, so we'll put our 0 there. Now I'm going to finish off part A of this, the acceleration of the block, and then I'm going to show you how we work backwards to find what that normal force is going to be. Okay, so sigma fx. Nick, I'm going to give you the complicated part here.
Okay.
What is it going to be?
I think it's 98.
I'm pretty sure it is too. 98 newtons. Okay, So now we can go ahead and find AX. That's going to be pretty easy for us. Our 98 newtons divided by the mass of our block, okay, which was given to us as 20 kilograms. Hopefully should be a relatively simple calculation. And Justin Hampton, when you got it, you let me know, please.
4.9.
Okay, good. And appreciate everything there. 4.9 with units of meters per second squared. Is that a positive rate of acceleration? Absolutely. Does that make sense given the problem that we have? Is it going to accelerate on our newly found x-axis to the right? Absolutely, it should. We would be concerned if there's no other forces if it would be accelerating up the incline. That would be a big issue for us. Okay. Here's the deal about normal force, though. There is no equation at this point that we have that's our magical normal force equation. We will always have to do the same thing if we are trying to find normal force, and we will have to work our way backwards, starting from acceleration, to figure out what that would be. Now, this problem is a little easier to do. What is the acceleration of our block along our y-axis? Is it going to accelerate off the incline or through the incline? No. So what's it going to be? I heard one person say it. How about all of us now? 0. Okay? That'd be 0 meters per second squared. So let's work our way back from that. If the acceleration has to be 0, what does the net force have to be? Also be 0 newtons. Because if this net force on that axis was anything other than 0, we'd have an acceleration along that axis. Now again, this problem is a little easier in this regard. Now we need to ask ourselves the question, and I'm going to phrase this the right way so it solves all of our problems for us, not just what we do here. What I want you to do to find the normal force is to add up what's here in the y column. Pretty easy to do right here. But we add up what's here in the y column and switch the sign. Again, there's not much to add up, so it makes it easy. And when we switch the sign, what do we get? Positive 169.741 newtons. And that would be our final answer. I'm okay with you leaving that in the table without having to write that out separately. Well, why do we have to do it that way? Add up what's there and switch the sign. This just happens to be a problem where we only have two forces acting along the y-axis. If we were to have other forces that would also have y components, we'd have to consider all of that because the sum would still have to be 0 in this case. I'll let you know, we also could do this, as we'll do a little bit later, when the acceleration is not 0. If we knew the acceleration was, let's just say, 2 meters per second squared, well, we could figure out what force would give us that acceleration, and then the sum would have to be that, whatever that value would be. Okay? Not there just yet, and that's okay. Any questions on sample problem 2? All right, sample problem 3. Good, a free body diagram that you guys have done before. Go ahead, out to the side somewhere, go ahead and draw our free body diagram, please. All right, Melody, give us one force that you have in sample problem 3. We have the weight of our sled, which would be right here in the center, pointing straight down. Excellent. Megna, what's another one, please? Okay, we do have the normal force, which should start from the bottom surface and point upwards. Good. Elson, give us another one, please.
FA.
We already have the normal force, and we have the weight.
F. Friction.
We have friction, the FFR. Where would that be?
Down
The bottom, and pointing to that, you said it?
there.
Left. Okay, so we would have our frictional force. Okay, Natalia, what's the last one we need? We have our tension force, good, which is at an upward angle. Here's what I would like for us to do now. Now that we kind of know a little bit from the last problem, we are actually going to show the components to this one. So we would have FTX and FTY. That way we understand that that's kind of how that right triangle would be set up. Okay, that's our free body diagram. So, let me ask you this question. Do you think it matters the order at which we put our forces in our table? No. Because what are we doing in the end? We're just adding up all the components. So it doesn't really matter what order. So I'm just saying that because later, if I put an answer key up and you have your forces in a different order, it's perfectly fine. It doesn't matter. Because all we're going to do from this stage down to the sigma f's is exactly that. We're going to add them up. Okay? So I'm going to put the weight and the normal force there. You can have them in a different order, and that's perfectly fine. Okay? Then we'd have the tension, and then we would also have our frictional force. Okay? Before we get rocking and rolling with things, I think it's easy. Identify the components that are zeros. That way we don't make the mistake of putting components in the wrong spots. Okay? So let's start with friction. Does friction have a component that is 0? Which one? Its y component is 0. So for force of friction, y component, goose egg. Okay? Maybe take a look at the weight in this problem. Does weight have a component that would be 0? Its x component would be 0. So we put a goose egg there. Alicia, what about our normal force? Okay, it would have an x component of 0. Paige, our tension force, where's the 0? Good, there is no 0 for it, but it has both an x and y. So we'll figure out what that is, and we'll get to that in a minute. Okay? All right, let's start with what I think is going to be, oh, I'm sorry, we got one thing to do. We are told if the force of friction is 25 newtons, hooray, we can just go ahead and put that into our data table. So we would just put it in as 25, right? No. Thank you. We have to look at our free body diagram. What direction is that frictional force pointing? To the left. Okay? So we have to include that as a negative 25. Okay, we have 3 components to calculate. This one is actually going to be easy in this problem. We don't have to do mg sine theta, mg cosine theta. I know there's an angle in the problem, but does the angle pertain to the weight? Nope. Angle pertains to that tension force. So we'll have to use that with the tension force. How do we calculate an object's weight? Very simple. M times G. So if it's not on an inclined surface, this part of the process is very easy. Okay, we're told that the daughter and the sled have a combined mass of 40 kilograms, all times 9.8. Pluggy chuggy. And Michaela, when you have your answer, let me know. Okay, 392, so we'll go ahead and we'll put that into our table as 392. Yep, it is negative. You calculate it, as you did, Michaela, as I asked, you calculated it to be 392. So we do have to go ahead and look at the free body diagram, what direction is the pointing. There we go. You can, but I want to get you out of that habit. Because when we get to some of those inclined problems especially, it's not always going to be both components will be negative. We saw one where we had a component that was positive. Now here's the thing about weight. Weight will always pull you down. It will never pull you up. So the y component will always be negative. It's just that depending on which way that incline might be set, one component might be positive or it might be negative. So I don't want us to automatically assume that the components as a whole would be negative for that. Which is why here, let's just put it in as 9.8 and we'll go from there. We know, based on the direction of the gravitational force that we call, that it should be the downward direction. But it's more so for those incline problems. Let's just use 9.8. Okay. All right. Normal force, we're not going to know what it is. We have to work back through it in the end. So we do need to figure out these tension force components. So, to find the tension's x component, let's take a look at it. Here's our right triangle. Is the x component the adjacent side or opposite side? It is the adjacent side. So we will take our hypotenuse, which is this. We know that information, and we will multiply it by the cosine of theta. So understand here we are back to, because there's something that is an angle measured with respect to the x-axis, that our tension is going to be multiplied by the cosine of theta. Okay, so we know the man applies the 95 newtons, so 95 times the cosine of, I decided to try to keep it easy on you with the trig today, cosine of 30. Pluggy chuggy. Emily, when you have your response, please let us know. .272 newtons. Okay? Is that going to be positive or negative when we go to put it in our table? It should be positive. It's pulling us to the right. Okay, so FTX, 82.272. Did everyone see how we got the x component here? I know I'm writing out a lot of stuff for you, but in the processing piece of it, do we understand why we're back to cosine? All right. FTY, our hypotenuse times the sine of theta. So effectively the same substitution, 95 times the sine of 30. That, again, should be pretty easy for us, for those of us that know our unit circle, but for those of us that don't, that's okay. Michael Taylor, what do we get?
47.5 newtons.
Yep, 47.5 newtons. Is that going to be positive or negative? It will also be positive. So, 47.5. Okay, like I said, we'll get to the normal force in a little bit later. What is that tension doing? Okay, just I want to make a point about this because of what the components are talking about. Is part of that tension force pulling to the right? Yeah, absolutely. Okay? It is what's going to help accelerate this along the horizontal axis. Is part of that tension force attempting to lift this object upwards? Yes, it is. Okay? Do you think that that's going to impact the normal force that the ground has to push back up onto the object with? Because we do have a force that is also in part lifting on the object. It will. It will have an impact on it. That's why I phrased things a certain way in our last problem, and we'll come back to that again. So let's finish off what we need in terms of our x-axis. Let's get our acceleration. So why don't you go ahead and follow it through? Okay? Sum up the forces on the x-axis, solve for the acceleration. Go. Okay, we hopefully find the net force to be 57.272 newtons, and then the acceleration 1.432 meters per second squared. How does that finish it up? Does that seem like a reasonable rate of acceleration for someone pulling their daughter in a sled? Yeah, it's reasonable. It's not like it's a very, very high rate of acceleration. Okay, so let's start with this. I understand that yes, part of the tension is pulling up on this sled, but is the sled going to accelerate vertically? No. We'd probably have to be told if it were, okay, but there is no acceleration along the y-axis. So what does that tell us the sum of the forces have to be on the y-axis? It also has to be 0 newtons. Now in the previous problem, what a lot of you did, even though I tried to ask you to think of it a certain way, is you just took the number that was there and switched the sign. Okay? I will reiterate what we need to do. Take a look at these force components that we have, add up what's there, and switch the sign if we have to get to a net force of 0. If we had to get to 100, it would be a different story. But add up what's here. So what's here? Negative 392 plus 47.5 plus 0, and switch the sign. That will give us the number that we put in for the normal force. That would give us a sum of 0. Again, if the sum was to be something other than 0, which it could be, we may have to do something a little different. Okay? So, Catherine, we do that, what do we get?
344.5.
Okay? 344.5 newtons. Should that be a positive force?
Yeah.
Absolutely. Okay? Normal force in this case is pointing in an upward direction. Okay. To reiterate it again, that normal force, we're never going to have a magical equation to go ahead and find it. Okay, these early stages of Newton's laws, we have to work our way backwards to go ahead and figure it out. Okay, I know there's a lot of sample problem stuff that we've done. Questions at this point? Okay, we're going to do one more together, okay, as our introduction. Okay, sample problem 4, and I'm going to kind of do this in a little bit different way. I'm calling it 4.2. We used to do it in a 4.1 way. So here we go. This is going to be a little bit different in its application. We're going to talk about the concept of real and apparent weight. Real weight would be, well, as I stand here, it would be the downward force that I end up applying on the ground. Okay? I'll say that for me, in English Standard, I'm almost exactly 200 pounds, so I have 200 pounds of force that pushes down onto the ground. Okay, we convert that to newtons and go that direction. But there are situations that might arise where you accelerate vertically. Maybe in an elevator. Maybe that first couple seconds of an elevator ride, whether it's ascending or descending. That's one of the things we're going to deal with here. Or if you're ever on an amusement park ride, like I think like the drop zone down at Kings Dominion or something like that, and you feel a difference in your weight. It doesn't mean that your weight is actually changing. It is just appearing to change. And we can figure out, okay, rates of acceleration and things like that based on what's happening here. One thing, though, we need to establish before we get to the problem. When you stand on a scale, believe it or not, your scale does not measure your weight. It measures the normal force it pushes back up onto you with. Now, if your bathroom floor, which is where you stand on a scale, is not accelerating, are those two forces equal? Yes. Okay? But what the scale is actually measuring is with what quantity of force do I have to push back up on whatever it is that's on top of it. And that's how it measures your weight. Okay? So, real quick, is the scale reading during acceleration going to be greater than, equal to, or less than the scale when the elevator is at rest? Okay? So let's say you have a mass of 75 kilograms. We're going to stand on a bathroom scale in an elevator. Why? Of course. Why not? You guys don't do that normally. You don't go into an office building. You know, go ahead, plop a bathroom scale down in the elevator, and then just go ahead and stand on it and see what happens. We're going to do that here in school later. Now, we're going to observe what happens during when that accelerates. I also need you to know that with elevators, typically they're designed, they only accelerate during the first and last second of its travel. It is actually not accelerating the entire time. It just accelerates right at the beginning, and then you travel at a constant speed, because that's what's safe. Okay? And then right at the end, when you arrive at whatever floor it is you need to go. So, the scale reading is going to be equal to whatever your actual weight is when your acceleration is 0. Anytime the acceleration of the elevator is 0, your weight is going to be, your apparent weight is going to read exactly the same thing as what your actual weight would be. Okay. It is going to appear to be less when the acceleration is negative. And on the vertical axis, okay, if you are accelerating downwards, your apparent weight is going to appear to be less. And it is going to be greater when the acceleration is positive. Trick question, but not really. When the elevator is at rest, is it accelerating? No. Okay? So it would read what your weight would be. As you are traveling at a constant speed, what is your acceleration? 0. The way that this scale would read, and I want to make sure you know this, is going to be exactly the same whether it is at rest or whether it's traveling at a constant speed. It is only in the moment of acceleration it would read something differently. Okay, so real quick, okay, all of this is about the interaction between weight and normal force. Okay, if we're doing a free body diagram, and I don't want to necessarily worry about whether it's accelerating or not, because the diagrams would be different, a little different depending on the scenario. We just have these two vertical forces affecting. Okay, so here we go. In part B, which we'll use this left table for. What does the scale read when the elevator accelerated at 2 meters per second squared? Okay, well, let's figure out what your weight should be. If we needed to know your weight, Fg would be equal to m times g. Well, it's just going to be our 75 kilograms times 9.8. Please go ahead and find your weight if you had a mass of 75 kilograms. Anuj, what do we get for our weight?
735.
Okay, so that would be 735 bananas. Newtons, that's correct. Good job. Okay, now, on our table, our weight, I hope we understand, we're not dealing with anything along our x-axis, so all of that is 0. We're dealing with stuff along our y. Now, 735 would go in here as our y component. But what direction is it pointing? Down. So now here's what I want us to be able to do. Okay? Notice how I've kind of set up these tables a little bit differently at the bottom. I've done this to kind of help you at the very beginning. We need to find the sum of the forces acting on the y-axis. This is a case where it is not 0. Why? Because we know that we are accelerating at 2 meters per second squared. And if you have a mass of 75 kilograms, please don't touch your calculators. What is 75 times 2? That is 150 newtons. So that means the sum of the forces has to be 150 newtons. So the question would be, what would the normal force have to be in order to add up to positive 150? Okay, we effectively would add the 150 to the positive 735. And Nick, you said it was? 885 newtons. Okay, so that's what the scale reads. The scale reads the normal force. Okay, very similar situation for part C. Very quick with our table. Weight, normal force, zeros, all through that. Okay, but now we have 75 kilograms times an acceleration of -2, which would give us a sum of, or sorry, yeah, a sum of -150. Okay, so if we started at -735 and we needed to get to -150, what would the normal force have to be? What would that be? Paige, why don't you help us out here?
585.
Good. It should be a positive 585 newtons. And again, that would be what the scale would read. As we're measuring the normal force. One last little bit. What would the scale read if the elevator itself and the scale and you were in free fall? I know we would have greater life issues if all of us are accelerating at a downward rate at -9.8 meters per second squared. But in that moment of clarity that I know you would have, what would the scale read? Think of it this way. What would be the downward force that you would be applying on the scale if you and it were accelerating at the same rate? 0. So how much normal force would have to push back up on you at that time? 0. So the scale in free fall would read 0 newtons. Everything is accelerating together at the same rate. And then we've got it. Well, that's okay. You would understand that.
Because you're pushing down 90?
No. You're not. In free fall, everything's accelerating downwards at the same rate. So if you're it's almost as if, well, that's a bad example. I won't say that. Okay? If you're all accelerating downwards at the same rate, you're not applying any additional downward force on anything, nor are things applying force back up on you. It's just simply traveling almost as if there's no force acting on it at all. It's not the case, but okay, it's all falling at the same rate.